And go ahead, please.
All right, welcome everybody. I'm Tim Hesterberg, and I'm talking about what every instructor should know about the Bootstrap. This is a program of StatPREP, which is an initiative of the MAA in conjunction with the ASA and AMA TYC. For this webinar, yes?
It's AMATIC.
AMATIC, thank you. The MAA is recording the webinar and retains the right to show it. And by participating, you agree that your contributions become part of the recording. Thank you. I want to introduce Catherine Kozak, who's the moderator. And if you have questions, please ask them in the Zoom chat. Catherine will moderate and share with me the questions. Grace Murrin from the MAA is the host for this meeting, and I'm the presenter. So why do we resample? Bootstrapping, permutation tests. Number one, to promote understanding that if you think about Stat 101, we start off by looking at data. It's very concrete. We're looking at things. And as we move on to the rest of the course, it becomes more theoretical, harder to understand. The resampling gives us concrete analogies to the theoretical concepts, and so we'll see that today. Second, there are fewer assumptions. Don't need to assume normality, equal variances, and because of that, it's more accurate. And finally, ease of use. We can use the same basic procedure for a wide variety of statistics, so we can do statistics when we don't have nice formulas. And this is very important in my own work at Google. So some of the statistical concepts that we'll look at are sampling variability, standard error, bias, central limit theorem, testing, and p-values. So let's start with some data. This is data from a student project. Barrett Rogers was comparing commercial time for basic and extended cable TV channels. This would be very relevant during this time of COVID. So his idea was that the basic channels, the ones that come with your cable subscription, will have more commercials than the extra pay cable TV channels because they got to make their money somehow. Well, wait, are you already paying for the cable subscription? Well, anyway, he collected some data and found that there were 9.2 minutes per half hour for the basic channels and 6.8 for the extended. So this seems to support his hypothesis. Now, are you as appalled by these numbers as I am? That's a lot of commercials. And here's the data. Oh, there's not a whole lot of data here. He only collected 10 random half hours of basic and 10 random half hours of extended programs. As a matter of fact, he didn't even do that. He got his girlfriend to do half of it. He could only stand to watch so much random TV. So we will start simple by bootstrapping a single sample mean, just one of those two data sets, and talk about the idea behind bootstrapping. And later we'll do two samples and we'll do a permutation test to compare them. So the basic bootstrap procedures, you repeat, say 1,000 times, 10,000 times. You draw a sample of size n with replacement from the original data. So 10 observations with replacement from the 10 basic TV channels. And calculate the sample mean for that random sample size 10. Do that 1,000 times, so you get 1,000 bootstrap sample means. And these are the, quote, bootstrap distribution. So here's what that looks like for the basic TV. And this looks nicely normal, centered at about 9.2, which was the mean of the original data. We get an idea of the spread of this distribution. And when we see something like this, it's very natural to compute the standard deviation of this. The bootstrap standard error is, in fact, the standard deviation of that sampling distribution. Let's talk a little more about that. What is a standard error? A standard error is how much a statistic varies. And we see that directly here. This is how much the bootstrap mean is varying. This is not the original data, this is the bootstrap mean. This is how much a mean varies. So this demonstrates what a standard error is. in a way that's much more understandable to students than a formula, S over square root of n. And frankly, I get people interviewing for jobs at Google who do not understand what a standard error is. I ask them about a standard error in the context of a regression problem, and all they can tell me is the formula for standard error for a sample mean. They don't understand the concept of standard error. So here we see the concept. It's how much the statistic varies. Second, we can estimate the bias. Now here we're working with a sample mean, so there's actually no bias. But the bias estimate from the Bootstrap is we take the average of the sampling distribution minus the observed statistic. So one of these, the circle, is the original mean. And then the dotted line is the average of the data. They're just about the same. They differ only due to random variation. So we have the observed, the mean, the bias estimate, and the standard error. So here we have both distributions for the basic channels and for the extended. Mean at the original mean. This one has its mean at the original mean. This one seems to be more spread out, and that's because the data is more spread out, so our standard error ends up being bigger. And they both look approximately normal. Now, the idea behind the Bootstrap is what we call the plug-in principle. The underlying distribution is unknown. We'll substitute our best guess. The plug-in principle is very common in statistics. We use it all the time. We know, for example, that the variance of a sample mean is sigma squared over n, where sigma squared is the variance of the population. We don't know what sigma squared is, so we estimate it using the sample variation, s squared. What's different with the Bootstrap is we're substituting for the whole distribution. So here's what that looks like. What we would love to do is there is some population f, and we don't know what it is. But what we'd love to do is draw many samples from that population, compute the statistic like x bar for each of those, collect all of those statistics, and those then comprise the sampling distribution for the statistic x bar. There's a problem with that, which is we can't draw lots of samples from the population. That's expensive. What we have is just one sample. So in the Bootstrap, what we do is we draw many samples from an estimate of the population. Typically, this is just drawing samples from the original data, but there are cases where we might do a parametric Bootstrap where we fit a distribution and then draw samples from that distribution. So we then draw many samples, and after that, do everything like we do in real life, compute the same statistic to get the sampling distribution. So here we have, at the bottom right, an example of a Bootstrap distribution. Now note that the Bootstrap distribution is centered at x bar, not at mu. And this is a big deal. This means we do not use the Bootstrap to get a better estimate for mu, because no matter how many Bootstrap samples we take, they're going to be centered at x bar, not at mu, plus a little random variation. So the Bootstrap is not creating data out of nothing to get a better estimate. Now, some people are suspicious of the Bootstrap because they think it's creating something for nothing. And the name doesn't help. The name Bootstrap comes from the adventures of Baron von Munchausen, this fantastical story where at one point the Baron is in the bottom of a well and he's gonna drown. Situation hopeless, until he comes up with the idea of pulling himself up by the bootstraps. Lifting himself out of the well, situation solved, something out of nothing. Yeah, well, that's not what we're doing with the Bootstrap. What we're doing is using the data twice. The same way in classical statistics, where we use the data first of all to compute x bar, And then second, to estimate a measure of spread, S over square root of n. Here, we're using the data twice, first to compute X bar, and second, to bootstrap to get an idea of the variation. So the fundamental bootstrap idea is that the underlying distribution is unknown. We substitute our best guess and then draw samples from that. And this generally works. Well, not always. And in particular, the bootstrap distribution is centered at X bar, not at mu. And it also matters for accuracy what we bootstrap. In a way, what we're bootstrapping is not theta hat itself, but the difference between theta hat and theta. We're using the bootstrap to get an idea of how spread this is, not the center. Well, instead of that, we might bootstrap a t statistic, a theta hat minus theta over a standard error. We'll see that later. Now, the bootstrap is implemented typically just by random simulation on the computer. In principle, we could do the exact bootstrap. If we've got a sample of size 10, there are 10 to the 10 possible samples, and we could enumerate all of them and get an exact bootstrap distribution that way. But for any reasonable n, that's impractical, so we do random simulation, typically 1,000, 10,000 samples. Moving on to another example. This appeared in Science related to bushmeat hunting and wildlife declines. So over a 30-year period, they estimated the biomass of 30 species, elephant, wildebeest, etc., in the national parks. So they went and counted how many elephants are there, what's the average weight of an elephant, multiply those, that gives us the biomass of elephants, add that up across the species, and related that to the fish supply in terms of kilograms per person per year. And the idea was, in years where there's less fish, then there will be more pressure for other food and more illegal hunting in the national parks. So the data looked like this. In the early years, the per capita fish supply, 30 kilos is about 66 pounds, 40 kilos, about 90 pounds, a fair amount of fish per person. And then when that starts declining and it's lower, and what we see is in the early years, when there tends to be a lot of fish, the wildlife biomass is relatively high and stable. And when the fish supply declines, the biomass declines. And so the authors did a scatter plot of the per capita fish supply versus the percent change from one year to the next, and found that in years when there was a lot of fish, there tended to be even an increase in wildlife. And in years where there was less fish, there were sharp declines, even including a 22% drop in a single year. That's scary. And they fitted a regression line. So our question is, how accurate is that regression line? How much does it vary just because of some randomness in the data? So to bootstrap this, we draw a sample of size 30 or 29 from the data. So that means that some observations will be included, say once, this one is included once. Some observations will be missing, like this one is missing. Some observations included multiple times, like this one was included 3 times. This is called a sunflower plot. The number of petals indicates the number of replications. And we then can draw a regression line through this bootstrap sample. And here's what the variation looks like when we draw 30, 40 bootstrap samples. We get an idea of the variation of those regression lines. How precise is it? And we see, it appears the point of minimum variation is about here. The further we extrapolate to either direction, the more variability there is, the less accurate the answers are. So this is nice to show students that the more you extrapolate, the less accurate your answers will be. Now, compare the picture that we see here to the standard formula for the variance of a regression line, which looks like this. And sort of the key point here is that this is at a minimum when x equals x bar, which is around here. And that's not the picture that the Bootstrap is giving us. And the reason is that the formula assumes equal variance at every value of x. But that's not the case with these data. If we go back and look at the data, we see that when there's a lot of fish, there's not a lot of variability above and below the regression line. But when there's less fish, there's more variability. And if you think about it, that makes sense in practice. When there's a lot of fish, then there's not a lot of pressure for wildlife meat, and hence not a lot of variability in it. But when there's more demand, then there's also more variability. So here, the Bootstrap isn't making the same assumption of equal variances that the classical estimate does, and hence it's giving a different answer. Now, another nice thing about the Bootstrap is it can give us estimates for quantities that are hard using formulas. For example, here, one thing that matters is the y-intercept when this line crosses 0, because that y-intercept tells us an estimate of how much fish we need to not lose wildlife, to have 0% drop. And so the Bootstrap distribution of that looks like this. It's the distribution of where these lines cross that axis. And we see that this distribution has a long tail. It's not normal. And the reason for that long tail is if occasionally you get a flat regression line and it takes a long time for that line then to hit the intercept. So we can do the Bootstrap even for non-normally distributed statistics. Moving on, the two-sample Bootstrap. Basic idea is pretty simple. If we had two independent simple random samples from two populations, then the way we Bootstrap is we draw samples of size n1 from sample 1 and n2 from sample 2 independently, and then compute whatever statistic we're interested in, like the difference in means. And then the 1,000 Bootstrap differences in means are the Bootstrap distribution. So that's what this looks like in this case, the difference between the basic and extended commercial times. An average of 2.2, which was the average of the original difference in means, and we get an idea of the spread of this. Now, we see that the variation doesn't cross 0 very often. So this is a hint that that difference in means is statistically significant. The difference is bigger than we would expect just by random variation alone. So let's talk about confidence intervals, and I'm going to start with a couple quick and dirty confidence intervals, and later we'll see another one. The Bootstrap percentile interval is you just take the middle 95% of the Bootstrap distribution. So that goes from about here to about here. That gives us a nice visual confidence interval for what is sort of the normal spread. How much could we expect the true value to differ from the current value above or below? And a t-interval computed using a Bootstrap standard error is you take observed plus or minus a t value like 2 times the Bootstrap standard error. And so in this case, that gives this, which is a little bigger interval, wider interval than this. And later on, we'll see another Bootstrap interval. Now, I will mention that those two quick and dirty intervals are really not very accurate for small n. And this is kind of unfortunate because people tend to think of doing bootstrapping when they don't want to rely on the central limit theorem, when they've got a small sample and they don't want to trust that the mean would be normally distributed. But it turns out that for small samples, these quick and dirty intervals are too short. The percentile interval in particular is roughly like doing x bar plus or minus z sub alpha over 2, not t sub alpha over 2, times not s over root n, but something smaller. It's sigma hat over root n, where sigma hat is computed like s, except using a denominator of n instead of n minus 1. And the reason for that goes back to the basic idea what the Bootstrap is doing. We're substituting an estimate of the population for the population. What we're substituting is the random data, the n observations. So if you think about that empirical distribution, it has probability 1 over n at each of the x sub I values. And the variance of that population is this, the sigma hat squared. It's not s squared. So we're drawing Bootstrap samples from a distribution that has this variance, and hence the mean from those Bootstrap samples has a variance sigma hat squared over n. And so the Bootstrap standard error, once you take an infinite number of samples so there's no random variation, ends up being sigma hat over root n, not s over root n. So it's a little smaller. And the usual t interval corrects for that by using a divisor of n minus 1. And it corrects for the random variation in this estimate by using a t quantile instead of a z. So there are 2 fudge factors. And the Bootstrap percentile interval doesn't have those. So it ends up being too narrow. The other quick and dirty interval, where we do a t interval but using a Bootstrap standard error, has the t fudge factor, but it doesn't have the n minus 1 fudge factor. So those intervals end up being too narrow. So here is how far off they are. Imagine we're doing a 95% interval. So we want to miss 2.5% of the time on each side. And in the easy case, where the true distribution is normal, this figure shows on the x-axis the sample size, and on the y-axis the fraction of time that each interval actually misses. So we would like it to be 2.5%. And the percentile interval, indicated by a p here, misses a lot more than that. For small samples, like 10 and 20, even 40, it misses way too often. It's really not very good. And the t interval using a Bootstrap standard error, which is indicated by a b here, is somewhat better in that regard, but it's still not very good either. In contrast, if we introduce fudge factors, then we get this e, and that's quite a bit better. I'll give you a reference at the end of the talk for what teachers should know about the Bootstrap that does give you the fudge factors. I'm not going into those now. And then finally, the Bootstrap t. This little t is the usual t statistic, and the big capital T is the Bootstrap t, and they're very accurate in this case. So to recap, these quick and dirty intervals are not accurate for small n. They tend to be too narrow. They're missing 2 fudge factors. All right. Incidentally, you may not want to go into details of that with your students, depending on the level of the students. So what we have so far is we see sampling variability. How much does a statistic vary as opposed to the data varying? From which we compute the standard error, we can compute the bias, and we can get quick and dirty confidence intervals. Next, let's look at testing and how accurate the central limit theorem is. So the idea when we do hypothesis testing is we sample in a way that is consistent with the null hypothesis, and the p-value is how often just random chance then gives us a value that's bigger than what the data gave us. So if the observed statistic, the observed mean was here, and random sampling gives us something bigger, this fraction of the time, that is our p-value for a one-sided test. So how do we do that for comparing two samples? Well, our null hypothesis here is going to be a little bit different than you may be used to. You usually may have a null hypothesis that mu1 equals mu2. The means of the two groups are equal. Here, we make a little stronger assumption. We assume that if the null hypothesis is true, there's no real difference between the two groups. Okay, not only do they have equal means, they have equal variances. Basically, the only difference between the groups is just random labeling. There's no real difference. Given this assumption, what we can do is we randomly pool the data because it's all from the same distribution. And then we resample by randomly choosing N1 observations without replacement and label those as group 1 and label the rest as group 2, and then compute a statistic that compares the two groups. Now, the name is permutation test. What we do there by randomly splitting into two groups is equivalent to permuting all of the observations and putting the first N1 into group 2, into group 1. So when we do that, pooling and randomly splitting, this is the distribution that we get. Now note that this distribution is centered at 0. We are now sampling in a way that is consistent with the null hypothesis. And this shows us the random variation that we get when there is no real difference between the two groups, and the only thing that's going on is random splitting into two groups. And the original difference in means was over here. This small fraction over here is the p-value. This is how often random chance alone gives us a statistic as big as the data actually gave us. So with about 10,000 observations, the p-value ended up being about 1/2 of 1%. So pretty statistically significant. Now, one nice thing about this is we can work directly with the difference in means. We don't need to switch thinking and talk about t-statistics, so it's much more natural for students. Okay, let's look at another example. This came from some consulting that I was involved in. This was consulting for Verizon. And Verizon was a telephone provider. And back when telephones in the US were deregulated, before that, Ma Bell gave everybody their phone service, both local and long distance. And it was partially deregulated. You still had one company providing the local service because you didn't want a bunch of different companies digging up lines to everyone's home. But other companies could provide long distance service. Now, suppose something went wrong. The local company was responsible for making repairs, and they were supposed to make repairs as quickly for the other company's long distance customers as for their own long distance customers. And this is overseen by the public utilities commissions of every state. So the incumbent local exchange carrier, in this case is Verizon, one of the competitive local exchange carriers is indicated by CLEC. Verizon made 1,600 repairs for customers that got their long distance service from Verizon with an average repair time of 8.4 hours, and 23 repairs for the other company's customers with an average time of 16.5. Ouch, that looks like Verizon is discriminating. Well, is the difference statistically significant? So here's what the data looks like. Histograms on the left, and we see that it's very long-tailed distributions, a lot of short times, and then a few long ones. Over on the right, we have normal probability plots where the y values correspond to the data, And we see that for the Verizon in orange, there are a lot of very short repair times, and then a few long ones. And similarly for the CLEC, a lot of short repair times, pretty low, and then, oh, there's one outlier. So maybe that difference in means is just due to that outlier. Well, even aside from that, we see that the repairs tend to be somewhat longer at corresponding quantiles. Now, there are odd bands here, and this is 24-hour periodicity. A lot of repairs made between 0 and 8 hours, not so many between 8 and 24 hours, and then again the next day, more repairs made. So if we bootstrap just one distribution, the large data set, we get a bootstrap distribution that's centered at the original mean, 8.4. It's got a spread from 7.5 to 9.5. Looks roughly normal. So this is the central limit theorem at play. With a sample size 1600, even though the population was very skewed, the sample mean is pretty normal. For the smaller data set, when we bootstrap it, the mean is at 16, like the original data, but the spread is much bigger. The other went from 7.5 to 9.5. This is going from 10 to 30. Why is this bootstrap distribution so much more spread out than the other? Well, there are two things going on. Most important is that there's a smaller sample. And with a smaller sample, the sample mean is more variable. Secondly, the distribution had a bigger standard deviation. So the bootstrap distribution is more spread out. And then the other thing that we see is that this distribution does not look normal. It's skewed. It's only 23 observations. That's less than 30. If we just had 7 more, everything would be all right. Maybe not. All right. Now, there was some non-normality asymmetry there. Is that a cause for concern? So if you look at this distribution, would this worry you, this amount of asymmetry? Now, if I were doing this talk in person, at this point, I'd ask people to raise their hands. About half the people would raise their hands that it's a cause for concern and half no. So let me share a story. I was working at a statistical software company. I got a grant from NSF to develop Bootstrap software. I got a supplemental grant from NSF to write a chapter for introductory statistics. And I hired a high school teacher and 2 college students to work with me for the summer on this chapter. David Moore was an author of an IntroStat textbook, worked with us. We prepared a chapter for his textbook. And one of the problems that we put in that chapter was basically this. We see this kind of bootstrap distribution. Is that asymmetry a cause for concern? And the publisher had a college teacher do the first draft of the solutions. And his answer was no, that would not be a cause for concern. And that's exactly wrong. He was used to using normal probability plots to look at data. And if this were data, it would not be a cause for concern because the central limit theorem would straighten things out. But here, this is the bootstrap distribution after the central limit theorem has done its one crack at straightening things out, and the bootstrap distribution is still very skewed. So this is a case where the central limit theorem is failing. This is not close enough to normal to use for inferences. It's a big cause for concern. Okay, here is the bootstrap distribution for the difference in means. And it's skewed. Now, what we have here is essentially mean of a very large data set. So that mean has very little variability in it, minus the mean of a much smaller data set. So the variability here and the skewness is being driven by that smaller data set. And That's in the negative of the difference, the x bar for the big distribution minus x bar for the small distribution, and hence we get the distribution that's skewed left here. And it's centered at the original difference in means. Now, interestingly, if we would work with trim means, something more robust, less sensitive to outliers, then the Bootstrap distribution looks pretty normal. We don't have that skewness, much less. And it's also got a much smaller variability. So for statistical reasons, we might prefer to work with trim means here rather than simple means. A nice thing about the Bootstrap is it lets us use the statistic that's best for the problem. We're not limited to statistics that have easy formulas. Now, in this particular case, this is overseen by the Public Utilities Commission. It's kind of an adversarial situation because if Verizon is discriminating, Verizon would pay big penalties. The opposing companies would get some of the money. Anything that hints of throwing away data is strictly verboten. So we did not use trim means. So just for comparison, the standard error for the difference in means would be 3.9, and for difference in trim means would be much less variable, standard error of 2.7. Now let's do a permutation test. So when we pool the data and take the difference, this is the distribution that we get. It's centered at 0, but it is skewed. Because again, remember, it's essentially mean of the big sample minus mean of the small sample. And that small sample was skewed right, so that difference ends up being skewed left. The original difference is here. This is the p-value. And when we do a test here, if we do the usual pooled variance t-test, we get a t-statistic of minus 2.6 and a p-value of 1/2 of 1%. Now, for a little more context, these tests are overseen by the Public Utilities Commission, and they're doing thousands of tests for different periods of time, different categories of service, different competitors. They do all of these tests at the 1% significance level. And if substantially more than 1% of those tests come out positive, then Verizon pays penalties. So in this case, the pooled variance t-test gives a p-value of 1/2 of 1%. That would be significant at the 1% level. In contrast, when we do the permutation test using 500,000 replications, we want to be accurate here. There's money riding on this. We get a p-value of 1.8%. which is not significant. These differ by a factor of 4. They can't both be right. So if you have the t-test giving one answer and the p-permutation test giving the other, which do you trust? Well, some historical context is when Sir Ronald Fisher was first proposing the use of t-tests, he stated that the t-test is valid only to the extent that it approximates the permutation test. It's a computationally efficient way to get an approximation for the permutation test, because the permutation test is just impractical using the computers of those days, which were young women. We don't have that same limitation anymore, and the p-value is the correct answer here because it doesn't require normal distributions. It doesn't, and in particular, it doesn't require zero skewness. And here we've got a lot of skewness. All right. Well, one of our samples is only 23. If it was only 30, it would have been fine, right? No, not really. Well, think about statistical practice. Our rule of thumb is if n is 30 and the data is not too skewed, then yeah, we'll do t-intervals and tests. And if not, okay, what are we going to do? We're going to do them anyway, because what else can we do? How bad is this? How big does n have to be before we're reasonably accurate, within 10%? So what I mean by that is if we're doing a 95% interval, we want to miss 2.5% on each side. So we want to be within 10% of that, between 2.25 and 2.75%. So how big does n have to be? And for an example, suppose we're doing a one sample mean and the population is exponential. What n do you think would give us reasonable accuracy here? 30? 50? 100? 200? Turns out you need 5,000. The central limit theorem operates on glacial time scales when you're working with the mean of one sample. For two samples with equal sample sizes, it's much better because the skewness between those cancels out. But for a single sample, if there's any skewness, and in practice there always is, then t statistics are not accurate. The central limit theorem operates very slowly. In contrast, Johnson, this is something that appeared in JASA 30, 40 years ago. It's a skewness adjusted t statistic, is far more accurate. So we ought to be using that. Or Bootstrap methods. Okay, so why don't people know this? For one thing, to really realize how bad things are, we need Bootstrap diagnostics. I'll show you some in a bit. And you need to do pretty accurate bootstrapping to really quantify how far off you are. And if I had wanted to do some of the simulations that I did for writing this paper, what teachers should know about the bootstrap, if I'd wanted to do that using the computer the department backs back when I was going through grad school, back when bootstrapping was hot, when it was relatively new, when people were looking at it, it would have taken about 20,000 hours for the simulations. We just couldn't do it back then. So what do people do? We've just accepted low accuracy, and we've learned methods from the people, from our professors, learn from their professors, et cetera, and we kind of adjust our criteria to fit what has been practical in the past. Okay, but let's look deeper. What is the distribution of a t-statistic? Now, there's theory that says if the population is normal, then X bar and S are independent, and the t-statistic has a t-distribution. And then there's reality. If there's skewness, then X bar and S are not independent. In particular, so say there's positive skewness, like for this Verizon data, for the big data set. So we have some big observations. And when we get a bootstrap sample with relatively many of those big observations, that makes X bar big. It also makes S big. And S is even more sensitive to the big observations than X bar is. So you get a positive correlation between X bar and S. And so what we can do is use the bootstrap to estimate what is the distribution of the t-statistic. So the t-statistic is X bar minus mu over S over root n. So we'll do the bootstrap version of that. We'll take X bar from a bootstrap sample minus the mean of this population we're drawing our bootstrap samples from, so that's X bar, and divided by S from the bootstrap sample over root n. And then instead of just using t sub alpha over 2, we'll use bootstrap quantiles, which for the Verizon data set are minus 2.11 and 1.79 instead of plus and minus 2. So they're not the same in both directions. And here's what that bootstrap t distribution looks like. It's centered at 0. It's got roughly the same variance as a usual t distribution, but there's a little bit of skewness. And if you just look at this, you might think that's not a big deal. and here's a t quantile plot, pretty straight. Except visual inspection here isn't enough. About 4% of the Bootstrap samples fall below t sub 0.025. So you think you're doing a 95% confidence interval, but really you're missing 4% of the time on one side and 2% of the time on the other. So visual inspection wasn't enough. We actually have to measure these things. So the Bootstrap t suggests that the usual t has one-sided non-coverage of 3.9%. Way off. And is this a general problem? Well, yes. When we're looking at the mean for skewed populations, or when we're looking at statistics other than the mean where there's some inherent skewness, if we're looking at logistic regression, etc. And there's also bias in these cases. So the Bootstrap t interval, the idea is, we're not going to assume that a t statistic actually has a t distribution. Instead, we use the Bootstrap distribution to estimate the quantiles. So the quantiles in this case were minus 2.11 and 1.79, and then we solve for mu in the equations we saw a bit ago, and that gives us an interval that looks like x bar minus the upper quantile times s over root n, and s minus the lower quantile times s over root n. And the result is we get x bar minus 1.79 and x bar plus 2.11, s over root n. So the Bootstrap distribution actually reaches a little further to the right than it reaches to the left. That might surprise you. Okay, remember the situation here. We're working with skewed data. We've got a distribution with some big observations. Call them outliers, if you will. Your intuition might be, I better downweight those outliers, reduce the effect of those outliers. When you do that, that would shift the mean left and make the standard deviation smaller. So your distribution, your confidence interval, if you're doing that, is going to be further to the left than to the right. But we actually need to do the opposite. With skewed data, positively skewed data, we need to reach further to the right. And here's how to think about it. The data tell us that the population is skewed. And when we do a 95% interval, we want to have a high confidence, a 95% confidence that we've got the true value within the interval. So we need to have high certainty. We want to have a small probability on each side that we're missing it. And in order to have that small probability, we need to think about what could have happened. And what could happen is our data might actually have too few observations from the long right tail of the distribution. And to protect against that, our interval has to reach further to the right to protect against that long tail. Here's how accurate different intervals are. The top is the easy case of a normal population. The bottom is the case of an exponential population. This solid line is how accurate the usual t interval is. For a 95% interval, we want to miss 2.5% on each side. And when the samples are small, 10, 20, 40, 100, it's way off. It's missing way too often on the right side. The P is the Bootstrap percentile interval. This is the usual interval that people usually think of when they think of the Bootstrap. And for really small samples, it's even worse than the T interval. And that's because it was too narrow. It's missing the fudge factors that the T interval has. Once we get to somewhat bigger sample sizes, 75 or bigger, then it's more accurate. But not a whole lot, it's still not great. Whereas the Bootstrap T, based on this, is much more accurate. It's getting close to 2.5% non-sided coverage much quicker than the other intervals are. So these 4 curves are for how often you miss on the right. These 4 curves are how often you miss on the left. And in all cases, the Bootstrap T is by far the most accurate of all these intervals. The Johnson T would be similar to the Bootstrap T. It's a skewness adjusted formula interval. All right, we're going to wrap up here. What have we seen here today? Well, the Bootstrap is great for helping students understand statistical concepts, sampling variability, standard error, bias, p-values, central limit theorem, because we see pictures that relate to all of these concepts instead of them being purely theoretical. Second, we've got flexibility. We can work with a statistic that is more robust. We could work with a difference in mean. We're not limited to simple means. We could use a trim mean. We could use a median. Think back to Stat 101, where we talk about means and medians. And we learn early on that a median is more robust to outliers than a mean is. But then later in the course, we try to ignore the fact that we ever heard of the median because we don't have easy formulas for working with it. Well, the Bootstrap doesn't have that limitation. And finally, it can be more accurate because we don't need assumptions like normal distributions or equal variance. But though for good accuracy, you do need to work with a Bootstrap T rather than the quick and dirty intervals. A permutation test, extremely accurate, and the Bootstrap T, quite accurate. So we've got pedagogical benefits of having concrete analogs to the abstract concepts. For testing, at least, it's straightforward in that we use the statistic of interest, like the difference in means, rather than having to work with t-statistics. And another advantage is we can check our work. Even if we do want to teach students the formulas, teach them the Bootstrap methods and the permutation tests too, so they can check their work and get some intuition as to what kind of answers make sense. And in practice, it's more accurate and it's more flexible, and we can use the Bootstrap methods in cases where it's hopeless to compute standard errors. And I run into this at Google, where we're computing statistics where in principle, I could compute a standard error, but in practice, I would mess up. It's really complicated, and I would check my answers using the Bootstrap anyway. So for further information, there's my website, and I'll mention in particular the article, What Teachers Should Know About the Bootstrap, Resampling in the Undergraduate Statistics Curriculum in the American Statistician. On the website, there's also the introductory statistics chapters for a few different books, and a link to a mathematical statistics text that I wrote with Lord Chahara. And that's it. Let's open it up to questions. Are there questions?
So, Tim, first I'd like to just thank you. That was very informative. I will let you know that there so far has been only one question, and that question was, will the recording of this be available? And yes, so as soon as the MAA finishes processing it, it will get posted on the StatPREP.org site under the webinars tab. So it'll take a couple days for that, but it will get there and be available.
Great.
Are there any other
Thank
questions? So somebody says, thank you, excellent talk. Thank you for your time and thoughts.
Thanks.
So we haven't had any other questions come in. So I guess I do have a question. Do you basically then, do you even worry about showing students the idea? Well, you don't teach, but would it make sense for me to show my students the quick and dirty ones, or just go straight to the Bootstrap T?
Oh yeah, we want to show them the quick and dirty one because those are going to be easier for them to understand and relate more to their experience. So when we start with the Bootstrap percentile interval, we're just starting with the Bootstrap distribution and using it to say what the variation is.
Okay. So you would show that
And
and then go and say, but it's not as accurate as if we did it this other way, and we then go to the other way.
yeah. Well, depending on the course. If it's an Introstat course, I may not do the Bootstrap T at all. For a course beyond that, then we want to do the Bootstrap T. Because in the intro course, we want to give them the basic ideas and not overload them. There's way too much that we try to put into that course.
Okay. I have an issue. My program has stopped working, and there have been some questions. I don't know if you can hear me.
I hear you.
But I can't look at the questions because my program stopped working. My Zoom has gone down.
I can look at Q&A.
Okay.
Would you recommend doing more statistical inference with the median in an Introstat course using the Bootstrap? Yes. I will mention that the median is kind of a special case where the Bootstrap has some problems with the median. And the reason for that is the Bootstrap is relying on the data to tell you what the shape of the distribution is. And when we're working with the median, it matters a lot whether we're working with a continuous distribution or a discrete distribution. And the Bootstrap, even if the true population is continuous, the data is discrete. And so the Bootstrap distribution will reflect that and be very discrete. And the Bootstrap, for small samples, reflects some peculiarities in the data. So the median is a special case, not so good. Trim means work much better.
Okay.
Would transforming data to make it more normal work? The problem with transforming data is now you're answering a different question. If your question is, are these two means different? Then transforming the data and doing a hypothesis test on the difference of transformed data is answering a different question. So really, we should have methods that answer the question we want to answer and that aren't so sensitive to assumptions. That said, if all you're interested in doing is testing, then sometimes transforming data is reasonable. If you're interested in doing estimation, then you don't want to transform the data. You want to answer the question that you were really interested in.
Okay, are there
percentile
go ahead, sorry.
Yes, go ahead.
No, go ahead.
Okay, the next question is, are percentile Bootstrap intervals worth using in an intro course? In what situations? Yeah, go ahead and use them because they're going to be easier for the students to understand and help them understand about variability. But it is probably worth warning them that they tend to be too narrow. Okay, teaching T distributions seems like we're lying to students. Why isn't Johnson's T more standard? I would like to see Johnson's T be more standard. It just never caught on. So T statistics are useful, but we should not pretend that they actually have T distributions. Okay, let's see. I think that's it for the questions.
Okay.
Are there other questions?
Well, Tim, thank you so much for your time and discussions today. This has been informative, and we will get this posted as soon as we can.
Okay, and I want to give a thank you to all the teachers who are doing the hard work of teaching students and preparing people who are going to be running our country in the future. Thank you.
Thank you, Tim. We appreciate it. All right.
Okay.
That concludes our webinar today. Thank you all for attending.